Have you ever wondered how to calculate the exact amount of paint needed to cover a curved 3D object? In calculus, we can find the surface area of a shape created by spinning a curve around an axis. This is known as a surface of revolution. This technique is essential in engineering and manufacturing. Whether designing a vase, a parabolic reflector, or structural components, understanding the relationship between a function's path and its resulting surface area is a fundamental application of integral calculus. To find the total surface area, we imagine the surface is made of infinitely many thin circular bands. Each band has a tiny width called ds, which represents the arc length along the curve. Summing these bands gives us the total area. Recall the arc length formula. A tiny change in the curve, ds, is derived from the Pythagorean theorem applied to the horizontal change dx and vertical change dy. This differential element is the foundation of our surface area integral. As the curve rotates, every point at height f, x, travels in a circle. The circumference of this circle is 2 pi times the radius. In this case, the radius is simply the value of the function, or f, x, at any given point along the x-axis. By combining the circumference of the rotation with the arc length element, we arrive at our general formula. We integrate from the starting point A to the ending point B to accumulate the area of every infinitesimal band along the entire surface. If we rotate around the y-axis instead, the radius of our circular bands becomes the x distance from the axis. The formula remains conceptually the same, 2 pi times the radius times the arc length, integrated over the appropriate interval. Let's apply this to a classic shape, the sphere. We can generate a sphere by rotating a semicircle around the x-axis. Using our formula, we can mathematically prove why the surface area of a sphere is 4 pi r squared. First, we find the derivative of our function. This represents the slope at any point and is a required component for our arc length element ds. Careful simplification here makes the subsequent integration much easier. Next, we plug the derivative into the arc length term. Notice how the terms simplify beautifully. The expression under the square root reduces to r squared over r squared minus x squared, which simplifies further when we take the square root. When we assemble the full integral, the radius f, x, and the denominator of the arc length term cancel out perfectly. This leaves us with a very simple constant to integrate over the interval from negative a to r. The integral of a constant is just the constant times x. Evaluating from negative a to a gives us 2 pi r squared minus negative 2 pi r squared, resulting in the famous formula for the surface area of a sphere, 4 pi r squared. Now let's look at a cone. By rotating a slanted line through the origin, we create a conical surface. This example will demonstrate how the surface area formula handles linear functions and produces the lateral area of a cone. Here, the derivative is a constant, 1/2. Our radius is 0.5x. We pull the constants outside the integral and focus on integrating x, which is a straightforward power rule application. After evaluating the integral at the boundaries, we find the lateral surface area. This represents the area of the side of the cone, excluding the circular base. Calculus allows us to find this for any angle or height. To summarize, always identify your radius based on the axis of rotation, compute the derivative for the arc length element, and set up your integral using the product of circumference and arc length. These steps work for any smooth curve. Before we finish, let's test your intuition. If we rotate the curve y equals x cubed around the x-axis, what is the radius r used in our formula? Since the radius is the vertical distance to the x-axis, the answer is the function itself, x cubed. Surface area is just one way we use calculus to understand 3D space. Next, you might explore volumes of revolution or even the strange paradoxes of infinite surfaces with finite volumes. Thank you for watching. Generated by Vision Solve AI.